All right, welcome. Happy Friday. Happy almost Halloween. Let's see here. Oh yeah, I wanted to show you because I just posted them, kind of bombarding you with assignments, but not really. We talked about the due dates and they're going to be nice and spread out. One thing that I'll have to adjust is I made a first presentation. So it's just the presentation that's going to have a grade. And so I posted the PDF as well as the RMD in case you find it helpful to have the RMD file. And so you're going to be submitting just the presentation, just the video presentation for that first one, just to get the hang of it. And then I can kind of have a look and see where you're at. And then what I decided to do was do an optional, let's see if I can. So the assignment for chapter 5, of course, is the same. So you've got your report and then you include your appendices, I guess. And so it's the same layout. And then I made it an optional presentation. So you have the choice of submitting a presentation for chapter 5 or for chapter 6, if you prefer, right? So you only have to do one of those for your second presentation. So that's why I wanted to post the chapter 6 assignment so you could have an idea, sort of, even though we haven't gone through all of chapter 6 yet, you can choose which one to do. So the presentation portion of chapter 5, it's going to be due quite a bit later, right? Probably at the same time as the one for chapter 6 because it's optional, right? So good. All right. So we haven't finished chapter 6, but I posted it there just in case you wanted to get a feel for which one you might like better, right, for doing that presentation. Okay, so we're moving along here. And what did we end off on? I can't quite remember. Okay, we have to have random samples so that our sample is representative of our population. Let it catch up here. And then we talked about, okay, a statistic is information that we've calculated from a sample, and then we're going to try to learn about the corresponding parameter. We're not going to know exactly what it is, but we're going to have some idea based off of our sample what it might be. Okay, and so inference is taking a statistic to learn about the corresponding parameter, right? And so we're going to have a statistic like X bar, so the sample mean, to try to learn about the population mean, right? So we're always trying to learn about the parameter. Okay. So just as a quick review, we must have a randomly selected sample. And we talked about the different ways that we could do that. It depends on if we have a finite population or an infinite population. But we must have a randomly selected sample in order for the sample to be representative of our population. To be representative of our population. Right. We also said that inference, right? The reason that we need our sample to be representative of our population is for our inference to be reliable. Okay. This is required in order for our inference to be reliable. And we said inference is when we take a sample to learn about the population, right? To get an idea of what the population looks like. So inference is using a statistic to try to learn about its corresponding parameter. Good. That's where we'll pick up. All right. Where were we here? Oh yeah, so the point estimate, right? Our statistic is going to be called a point estimate. And so it's going to be a calculation from the sample, but we call it a point estimate just as a general term. And it's going to be our best guess based off of our sample of whatever we're trying to learn about, whether it's the population mean or the population proportion, right? So then our sample mean is our best guess at our population mean, and our sample proportion is our best guess at the population proportion, of course. So let's see here. I'll bring this all in here. I can talk about it. Okay. So to estimate the value of a population parameter, right, we compute a corresponding characteristic of the sample. So that's going to be a sample statistic. Over here, we said just a statistic, but that's okay. Just underline statistic, right? A sample statistic. Statistic by definition is a measurement from the sample. So sample statistic is a little bit redundant, but that's okay. I think it's there for emphasis. So if we have information on, I can't remember what EAI stood for, it doesn't really matter, but we have salary information on a bunch of employees. So we have some sort of HR database, of course. And so we know everyone's salaries, and we also know some other things such as, oops, hey, how are you? All right. So here we have, I still don't know what EAI stands for, doesn't matter. They're employees of some sort. And so we have their annual salary in dollars, and we also have whether they completed some management training program. So of course, the salary is a numerical variable or a quantitative variable, and the whether they did training or no, or have done the training or not, that's going to be a categorical variable. All right. So here we'll say, oh, and I guess it's really small right now. So I'll zoom out. Salary is quantitative, and I shouldn't use an equal sign improperly, is quantitative, whereas the training, right, whether they've done training or not, right, the training is categorical. And we said, right, if you have a quantitative variable, then usually the thing that you're interested in is the mean, right? And so we can talk about the mean salary. It doesn't make sense to talk about the mean training because it's a yes, no categorical variable, right? And so then we start talking about the proportion. maybe the proportion who have completed the training, or the proportion who have not completed the training. Just depends on what you want to talk about, right? And that's going to determine how you find your sample proportion. And so it's kind of assumed that you know how to find the mean and the standard deviation. Of course, I'm not expecting you to calculate it by hand by any means. You can use a standard deviation calculator, or the most easy thing is to use Excel, of course. And so just as a note here, this is the sample standard deviation. Okay, so you have a choice if you're using Excel, right? Can't remember what the command is right now, but I think it's like standard dev.s or .p. So you'd have to use the sample one. And in general, we always use the sample one. Okay. So we can find the mean salary. We can find the standard deviation of the salary. These are all from the sample. So these are all statistics. Okay. If we're trying to estimate the proportion of employees, so the population proportion who have completed the management training program, then we count the number of yeses here, 1, 2, 3, I guess we find 19 out of 30 completed the program. So this is out of just the sample size, right? So it's a sample proportion. And I really don't like the bar. I usually use a hat. So if you're used to seeing a P hat, that's kind of more normal, I guess, but this works too, right? You just need to make that connection, move on with your life. So, so what we can do is we can compare the values. So if we have an HR database, for example, then we have information on all our employees, the population of employees, right? And so this is from a sample of size 30, right? But an HR database will have information on the entire population, right? So the reason, so we wouldn't need inference here. We know everything about our population in terms of HR stuff, but it's just to illustrate the procedure, right? If you don't know what the whole population looks like, then what are the tools that we can use? And so this is from a sample of size 30, but an HR database has information on all, I think later they tell us that it's 2,500 employees. And so I'm giving that to you now in this kind of roundabout way. Okay. So we can generate, this means we can find the parameters, right? The parameters are from the population. This means we can find the parameter or the values of the parameters Gonna have to put it on fresh page here. So once we have our population, right? If we looked at the population mean annual salary, we end up at an even 71,800. Okay, from our sample, we found an average of 71,814. That's our best guess, right? Assume you don't know what the population looks like. This is really close, or I don't know, reasonably close, right? And so that's going to be our best guess. Now, we don't know if our sample puts us close to the population or not, but that's where we go back to, okay, we have to have a random sample in order to even hope to be close to the population, right? And so same thing, if we compare the standard deviations, we get 4,000. So it's actually wider for the population than it is for the sample. And I find that really quite interesting. Usually that's not the case. Usually for a sample, it's a little bit wider. So I'm not sure what happened there, but that's okay. Fluke. Sampling error, we'll call it later, right? The difference between the population and your sample, we're going to call it sampling error. And then we can know that the population proportion is actually an even 60%. We found 63%, and we're going to be able to build some error bounds around these estimates to try to capture these values, right? It helps kind of seeing with them being known when usually that's not the case. Okay, so the problem becomes, okay, so here we have sample information. Now, put those 30 employees back into the employee pool and now draw a completely new random sample of size 30. We understand that these estimates would be different, right? And so then we put those guys back and we collect a new random sample of size 30. We might be reselecting a couple of employees just randomly, right? But overall, we have new samples of size 30 every time. And each sample is going to generate a slightly different point estimate, right? And so if a new sample of size 30 we're waffling here, is randomly selected. I'm gonna say is randomly selected. We would find slightly different point estimates, right? And so we would find slightly different point estimates. Got a hair going on here. Couldn't be mine. So need to wear a hairnet most of the time. So what we're going to be finding is that this develops a sampling distribution, right? And so if we continue to do this, or in theory, if we were to keep putting our sample back into the population, and then we collect a new random sample of size 30, and then we record the information that we get out of each sample, then eventually we're going to have a sampling distribution. Yeah. So this is the idea behind the sampling distribution. Ta-da! Sure. Let's just go for it. This should all be review, but it doesn't hurt to go over it again. They're really important concepts. And so that's why I'm going a little bit faster. But the textbook has really great examples all the way that I've kind of trimmed down quite a bit. because I just wanted to review the concepts. Okay, so for sampling distributions, it's this idea that if we collect a large number of random samples of size 30, for example, we're going to start to build up a distribution. So it's going to start to look like, drum roll, a normal distribution. Okay, and so that means that we're going to have a mean and we're going to have a standard deviation of this thing. And that's actually true for both the mean and the sample proportion with some assumptions that we have to check. But especially for a mean, if you think about, okay, so we take a sample mean from a sample, our first sample of size 30, right? We jot it down and then we put those guys back and then we take a new sample, we calculate the mean, the sample mean, we jot it down. That's our second observation. And then we keep going. And let's say we do that 1,000 times over, right? Our sample mean should be relatively close to the population mean, right? And so what we're going to find is that the expected value of the sample mean is the population mean, right? We expect our sample mean to be close to, or to be eventually, if we take enough samples, to be the mean of the population. So the sample means are all centered on the population means, are centered on the population mean. Just as a little side note, when the expected value of that point estimator is the population parameter, we say it's unbiased. And that's just good to know for terminology. Okay. Because sometimes that'll be the case where it says, okay, and this point estimate is unbiased, and then you're supposed to know what that means. So, and so what we say is that X bar is an unbiased estimator of the mean. Fine. What about the standard deviation? Now, the standard deviation, let's see here if I can grab all of this. All this stuff. Hey. Okay. So the standard deviation of X bar, what happens when we take a collection of sample means is that they're all going to be close to the population mean. Right, so we actually reduce our standard deviation when we're talking about the distribution of X bar. Okay. So since all X bars are closer to mu than individual observations would be, and individual observations would be our standard deviation of X bar will be decreased, right? It's going to be, we have less spread, right? We expect all our sample means to be relatively close to the population mean. So now we have less spread, and you can kind of bounce ahead here. There's a relationship with the sample size, right? As we increase our sample size, our estimate gets better. And so we get closer to the actual thing, so the parameter. So since all X bars are closer to mu than individual observations would be, the standard deviation of X bar is less than sigma, right? And so it takes into account the standard deviation, but then we divide by root n. The standard deviation of x bar is s over root n, okay, which takes into account the sample size, which takes into account the sample size. Right. As we increase our sample size, the estimate for the standard deviation of x bar is going to improve. So we don't have to talk about the standard deviation of x bar is the standard deviation of x over root n, right? That gets confusing. So instead, we call this the standard error. Of x bar. Oops. There. So the standard error of x bar is going to come from, it's going to use the standard deviation of the observations, right? And so S over root n. So even though we have this finite population situation over here, what we're going to say is that if the sample size divided by the population is more than 0.05, right? So then, oh yeah, that makes sense, sorry. If the sample size is more than 5% of the population, then that's when we're going to use this. But throughout the rest of the text, we're actually going to assume that n over, so lowercase n, the sample size divided by the population size or the approximate population size is less than or equal to 0.05, right? So it's going to be less than 5% of the population, essentially. And so then we just then end up using this infinite population calculation, okay? And so here, I'll put this over here, but unless, oh, maybe I'll use, so that puts us, lasso. Okay. So most of the time you should check, right? If you have a sample size, you want to make sure that it's less than 5% of the population, but that's usually going to be the case. If it's not, then you need to do this, shoot, what's it called? It's a corrector, finite population corrector, I think it's called. Oh, the correction factor. So if our sample size is less than 5% of the population, then we have to do it. But you can see that if capital N, so if the population size is a lot larger than the sample size, then it just basically goes to 1 over 1. No, n minus n approaches n minus 1. And that goes to 1, square root of 1 is 1. And then here we are here, back to S over root n, okay? So for our cases, we're just gonna assume that we can just use the S over root n, okay? So if we check, we have a sample of size 30, okay? And so 30 divided by 2,500 employees, that's 1.2% of the population, which is less than 5%. So we can ignore the finite population correction factor. So even though we have a finite population, we're still going to pretend that we have an infinite population because our sample size is so small in comparison. Oh. That's what I wanted to highlight. So then we have our sample standard deviation, right, from our one sample. So that's always going to be the case. We only have one sample. We construct the sampling distribution as if we collected thousands of these different samples, but we don't need to do that because it's already been established. So then we have the standard error is 611. And in this case, we could look at the population and look at the difference between the standard error of the estimate, so X bar, versus the standard error of the population. Okay. And so here, the difference between the sample standard error and the population standard error is due to the sampling error, right? Or the error that results from observing a sample of 30 rather than the population of 2,500, right? Okay, so from there, we can talk about, okay, so most situations, X bar is going to have a mean of mu, right? The population mean, and it's going to have a standard error of S over root N. And so all we need now is the shape, and spoiler alert, it's normal, right? And the reason it's normal is because of the central limit theorem. We now know the expected value of X bar is mu, and the standard deviation of X bar, which is the standard error, is S over root N in most situations. Right, if N over N is less than or equal to 0.05. Okay. So all that's missing is the shape. So we have the mean and we basically have the standard deviation. This we call the standard error of X bar. Okay. Now we learn that the shape will be normal. That the shape of the distribution will be normal as long as our sample size is large enough. As long as our sample size is large enough. So I think I have, yeah. So the central limit theorem is a big deal, and it's pretty cool. So the central limit theorem says that it really doesn't matter what population you're pulling from. So you don't have to be looking at stuff from a normal distribution for the distribution of the means to be normal. As long as you're collecting a large enough sample, then the sampling distribution of X bar is approximately normal. So that's really cool. And it's kind of mind-blowing. And so it brings the question, what's large enough? Well, if it's large enough, usually we say more than about 30. It depends on the population shape, okay, the distribution of the population. So N usually greater than or equal to 30. Okay. So as a little visual, we've got these guys here. So none of these populations, the population distributions, none of these are normal, right? But if we look at two different sample means, so from population 1, we've pulled 2 randomly selected samples and we have the sample means for each of those, right? Then this is the distribution of those 2 means. That's not going to be very helpful because it's just the sample of size 2. I mixed that up, but we're taking a sample. Yeah, I keep saying it, but it's, anyways, the sample size is 2. And then if we look at the distribution, the sampling distribution of the means, it becomes this. So here it becomes kind of wonky, but as you increase your sample size, right, even at a sample size of 5, we approach this kind of normal distribution. It depends on the shape that you started with in your population. And at a sample of size 30, right, all of these look approximately normal. Okay. So the central limit theorem, we usually abbreviate CLT. Okay. And so the central limit theorem, the CLT, says that any population distribution, or that the sampling distribution, I'll say, the sampling distribution of X bar approaches a normal distribution as the sample size increases. Approaches a normal distribution as the sample size increases. Regardless of the population distribution. This is regardless of the population distribution. Okay. So that brings me to, if we're pulling from an approximately normal distribution, we can relax that sample size requirement, because then if we're pulling from a normal distribution, it just makes sense that we're going to have approximately normal results, right? And so if the population is approximately normal, we can relax the sample size condition, right? We can collect a smaller sample and still be fairly confident that our sampling distribution will be normal. And so if the population is approximately normal, the sampling distribution will also be normal, or will also be approximately normal, even at small sample sizes. Right? Whereas if we have a really highly skewed distribution, then we need to increase our sample size, right? So here we've got this crazy skewed distribution in population 3. So we're collecting random samples from here, and then we're looking at the distribution of the means. So of course, at a sample of size 2, we're not getting anywhere. Even at a sample of size 5, there's still some skew here. But once we hit a sample of size 30, then we have a normal distribution. So even if we came from this really skewed distribution, by the time we hit a sample of size 30, we have a normal sampling distribution. So that's why we say, okay, as a rule, right? If we have a sample of size 30 or above, then we're safe. We don't need to think about where we pulled from because it can be a crazy skewed distribution and the central limit theorem will have kicked in. Okay. And so if the population is highly skewed, like population 3 above, right, or in the graphic here, we need a larger sample size to ensure the sampling distribution is normal, to ensure the sampling distribution of X bar is normal, right? But n equals 30 or n equals greater than or equal to 30 can handle, you know, even the most skewed distributions. This is why, as a rule, we say we need n greater than or equal to 30 for the sampling distribution to be approximately normal. To be approximately normal. Right? And that goes for any population. Can't remember if I had something. No. Okay. So if we think about a proportion, right? A sample proportion, now we have the number of successes divided by our sample size. And what's weird, but also really cool, is that these proportions, these sample proportions, if we look at them, so same idea, we have a sample of size 30, we record the sample proportion, and then we put those guys back in, and then we pull them out. And what happens if you kind of accumulate a list of sample proportions, those also follow a normal distribution, and they also have a mean, and they have a standard error or a standard deviation of p bar or p hat. Okay. And so one of the things to keep in mind with the proportion, just like the sample size greater than 30 ensures that the central limit theorem kicks in, we need to make sure that we satisfy some criteria in order to be able to assume the normal distribution for a proportion. So P bar, P hat, the sample proportion is, of course, the point estimator, and we know how to find it. And what we're told is that the expected value of the sample proportion is the population proportion. Again, not that crazy, because if we collected our sample of P of sample proportions, sample of sample proportions, meant what I said, and I said what I meant. Right, gets confusing, but if we have a sample of sample proportions, then we expect each of them to be close to the population proportion, right? So it makes sense that they would be centered on the population proportion. Okay, and again, we say that it's an unbiased estimator, and that's just because we expect it to be close to the population proportion. Okay, and so what we can do is we can talk about the standard error of P bar, or the sample proportion. Let's bring this in here. So again, right, the standard deviation of P bar, usually we just denote it as, or we call it the standard error of P bar, because it gets confusing, right? In this case, we don't have a standard deviation in the calculation, but just to match in the means case, right? So, and just like before, we will only use the finite population correction factor. Is that what we said? We would only use the finite population correction factor essentially for small populations, right? For n over n greater than 0.05. Move it down here. Oh. 0.5, that's something different. Okay, so most of the time we'll use this. And so even if you don't know what the population size is, unless you think that it's a really, really, really small population, then you can go ahead and use this infinite population calculation. Okay, and I think they even said that they're going to be, so we can ignore the finite population correction factor. And so what we have is the standard error of the sampling proportion uses the sampling or the sample proportion, and then 1 minus the sample proportion, which is basically, if the sample proportion is the proportion of successes, 1 minus P bar is going to be the proportion of failures, right? And so here, this is the proportion, and maybe I'll put it on here instead. Proportion of successes, and then zoom in so come on, to go out there. Oh my gosh, is it going to behave? This is the proportion of failures, right? 1 minus P bar. And then we divide by the sample size and we take the square root. And because we happen to know what the population looks like, we can compare our estimate, right, to our actual population parameter, right? And they're relatively close here. And so one thing that we need to check is some conditions. And usually I say 10. But the condition is that, okay, our sample proportion, the sampling distribution of P bar will follow a normal distribution as long as we have at least 5 successes and at least 5 failures. And I see I'm plumb out of time. But let me just jot that down here. Okay. And so we can assume P bar follows a normal distribution. If the number of successes, which is n times P, or usually we use n times P bar, is greater than or equal to 5, and the number of failures n times, no, let's not get crazy with the Q's, 1 minus P bar is greater than or equal to 5, right? And so we have to check this condition, but it's always going to be satisfied. And with that, I'm going to wish you a happy Halloween. If you have any questions, let me know. Otherwise, Enjoy the weekend.
Bye-bye.
See ya.